Hi everybody, welcome to today's Autonomy Talks. Today we are very happy to have Patrik Schmuck, who is a postdoctoral researcher in the Vision for Robotics lab here at ETH Zurich. A bit about Patrik. So he received a master in computer science from the University of Tübingen in 2015, and then he got his PhD this year in collaborative vision-based SLAM from ETH Zurich. Today we'll talk about collaborative perception for robotics, and I hope he will show us some cool videos about collaborative robots. Thank you very much.
Cool. Okay, can I start?
Yes.
Okay, cool. Then, thanks a lot for the kind introduction. Yeah, as already said, I will talk a bit today about collaborative perception, about robotic teams, and show a bit of my research and the research we're doing in the lab to enable robots to work together as a team and to perform SLAM as a team. And let's jump into it. I mean, SLAM has reached a quite high level of accuracy or of maturity in the meantime. It transitions more and more into customer products and real-world applications. And we can see here 4 very nice examples where we can use robots for household chores, for search and rescue applications, for inspection tasks, and also for industrial inspection, agricultural inspection. So all very interesting, very modern tasks for robotics. But yes, what we also see here, there's one thing that all these 4 videos have in common, and that is we see only one robot in each of these videos. And if you think about how would we humans usually approach a complex task, we do that in a team because we can be more efficient, we can maximize our strength. And of course, the same holds also for those robots. So today we want to see how we can enable robots to act together as a team. And so as the title already said, the underlying principle that we are using is SLAM. And since I'm not sure whether everyone is familiar with SLAM itself, which stands for Simultaneous Localization and Mapping, I want to use the first few minutes to give a brief introduction so that we are all on the same page. So what we have in SLAM is, there's 2 parts. So the first part is localization. So in our terms, this means we have a known representation of the environment, which kind ever, but we will call this representation our map. So for example, as depicted here, something that encodes the structure of the environment. And then we use this existing map to estimate our location inside it, but we will not modify the map. We take it as a given. And the other part is mapping. So as you might have imagined or already known, this is the exact opposite. So we know where we are, for example, from GPS measurements. And then we want to estimate our location inside this environment using, now we want to use this location to basically estimate the 3D representation of the environment. For example, this nice dense 3D reconstruction we see here in this image. And as the name says, simultaneous localization mapping is we're doing both things at the same time. So we have here this chicken and egg problem. Usually for localization, we need a map. For mapping, we need to be localized. And we always need to rely on something like some external measurements or some already known information. And this limits our autonomy. And here we see such a video of SLAM in the slide also. So we see the robot at this blue arrow. We see its trajectory as the golden line. And of course, we see a 3D map of the environment. And in an iterative fashion, it estimates how it moved, how the environment looks like. And with this, we have a complete autonomy. So we don't have to rely on any information that comes from external sources. So this is the basic idea of SLAM. And the 2 main principles nowadays, I would say, that are, let's say, prevalent in SLAM is LiDAR sensors or lasers or vision sensors, or we could simply say cameras. And I want to quickly show a bit the differences, because today we will focus on vision-based sensors that we also know why. So for laser sensors, a nice characteristic is from the laser rays, we directly get the distance of our scene, so the scene depth, how far a point in space is distant from our sensor. State-of-the-art lasers, like laser sensors for robots, go up to quite high range. So, for example, up to 300 meters. These recent 360-degree sensors. But of course, like if you know them, you know they're a bit bulky and heavy. They have a high power consumption, and they're also quite expensive in the end. So yeah, so they're not everywhere. Let's say like until we have a LiDAR on our phones, for example, I guess it will at least take a lot of time until this happens. And yeah, this is the difference when we look at cameras. So the first point is there's an incredible amount of information in such a camera image. Yeah, for example, like if you look at the image, you can see there's a tree, a car, a house, for example. Here, this is a well-known Kitty data set. It's taken in Karlsruhe, so if you know the city, you might also infer that from the images. There's so much information contained. And then, of course, an advantage of cameras is they're everywhere. So yeah, almost every device has a camera in the meantime, smartphones, cars, PCs. Yeah, this is a sensor that is omnipresent, and it has low power consumption, weight, and cost, which also, yeah, is one of the reasons why it's everywhere. The biggest disadvantage here is we cannot get depth directly from such an image. So we have to incorporate this in our estimation process and find other ways to estimate the depth of our scene. So as I said, we will focus today on these vision sensors, basically mainly because we can deploy them everywhere. They are everywhere. Low power consumption makes them available. So yeah, we focus on Visual SLAM. And if we speak about Visual SLAM, I want to quickly mention how we represent SLAM, how it looks like basically. We represent this as a graph. And yeah, this is indicated here. So from the camera, we get these images here, for example, 2 images looking at the same scene. And what we do is we combine this with a 6 degrees of freedom pose in space. So a position measurement and a rotation in space. And this together we will call the camera frame. This was a notion that we will use throughout the talk. And then we have 3D landmarks or map points. They are called a bit different in some different works, which encode yeah, some point in space, for example, a point on a wall. And yeah, then we can connect this to our frames using 2D feature observations. So this is the position in the image where this 3D point in space is visible in the 2D image. And yeah, so we have our 2 frames. We have the 3D landmark, and we can see the landmark in the image. So we basically draw a connection, an edge between these, yeah, between these frames and the landmark. And if we add some additional frames and some additional landmarks, and of course edges in between, we end up with a graph that actually represents our SLAM estimate of the environment. Now there's one last thing we have to say. So if we look at these frames, they all look pretty similar. So we don't want to keep all of them in the end. We only we drop some of them and keep the ones that we consider as the most important ones. So to illustrate it, we see here, like we drop these 2 frames and their connections, and what we keep is the frames that we will call keyframes. So basically you can imagine this as like the most important images from the camera. The other ones we drop. So this is also a notion that we will use throughout the talk. And yeah, then also for our graph, we add some edges between these keyframes to encode yeah, a temporal neighborhood. So overall, we are there with our representation, and then there's basically, we said it's a graph representation, so this has a special name. If we look only at these keyframes, we will call this a post graph in the end. And if we look at the whole graph, we will call the SLAM graph. So basically, post graph is only the keyframes without landmarks, and the SLAM graph with the landmarks. So this is our SLAM representation, but yeah, it's a bit abstract. So let's look at the video, how this actually looks like in the end. So this is OrbSLAM. It's yeah, a system from 2015, quite a seminal work when it comes to Visual SLAM. So we see in the top, the image with these 2D measurements, these 2D feature locations in green in the image. And on the bottom, we see actually the SLAM graph. So we see here in this blue frusta, this is the keyframes, and then we see the landmarks in black, and the ones that are in the field of view of the camera are actually also depicted in red. So this is actually like in a real world example how our SLAM graph looks like. And yeah, but this is for a single robot. And what we want to see now is, yeah, how can we achieve collaboration in a sense of perception? So the basic idea of collaboration is in the end that, yeah, we want to achieve a goal that one team member could not achieve on its own. For example, the time to get to a goal or the quality of the results. And yeah, in a sense of perception, probably like the most basic way of collaborative perception we can find is the stereo setup. So we have two cameras in a fixed constellation. And then if we take with these two cameras, each an image at the same time, we can use this to calculate the depth of our scene from simultaneous observations in these two images. So this is clearly a case of collaboration, since with one camera alone, we could not do this. With both, it's possible. But on the other side, of course, this is a fixed, it's a rigid setup. Yeah, there's not much more we can get from this. So yeah, in the end, this is not like the best or the end what we can get out of collaborative perception. So let's look a bit at other examples. So the next thing that we want to look at is collaborative mapping. So as the name says, we build a map with data contributed by multiple agents. So here in this image, for example, we would have two UAVs or two drones that are contributing to our map. So yeah, the good thing is here we can have a more efficient and more accurate mapping process since we have more data from more agents. But as it's indicated from these arrows, yeah, the map is not shared with the agents, so they cannot benefit from this nice and accurate map that we are building from their data in the end. So yeah, if we want to overcome this, the next step is multi-session SLAM. So here an agent can reuse a SLAM map that was built in a previous run. But the downside here is like only one agent can be active, which limits again our collaboration. So we have one agent, we build the map, and then the agent itself or another one can reuse the map, but not two at the same time. And yeah, if we also eliminate this limitation, we end up at collaborative SLAM. So we have multiple agents sharing data to build a map together. The map is shared back with the agents, so we have two-way arrows here. And this way they can have access to more than their own experiences at runtime, which promises a higher efficiency, higher robustness, and higher accuracy of the SLAM estimates. And this is what we want to look at today, how we can push the state of the art in collaborative SLAM closer to this promise to making the most out of every agent and its shared experiences. And yeah, for this reason, basically we have identified 4 essential aspects, or we call it here 4 pillars for collaborative perception. So what is necessary to develop SLAM systems that allow robots to collaborate and perceive their environment as a team. The first one is the architecture. So we have a system where multiple robots want to share data, want to contribute. So we need to think about the architecture that can enable this. And of course, with multiple participants, we need to think about like allocation of tasks and of resources in our system. As we've already said, we want to achieve data transparency so that agents can have access to more than their own information. And also an important aspect is we want to achieve platform independence. So the idea is here to not develop an algorithm for like one specific robot, but something that is generally applicable to different types. Another point is we want to go for real-world applications. So we want algorithms that are not only like feasible on data sets on one PC, but something that really runs with multiple robots in real-world examples, collaborative SLAM in real world. Talking about SLAM accuracy is a thing that we always have to look at, and in the context of collaborative SLAM, we want to especially see how collaboration can actually improve our accuracy compared to single agent SLAM. And also multi-agent systems, scalability is always an important aspect. So we need to think about scalability in size of the workspace, and also of course scalability in the number of participating agents. So the first thing we want to look at is the underlying architecture, because it's the foundation of the whole system. And before we dive deeper into it, I want to quickly draw an outline between swarms and teams of robots. Especially swarm robotics is a term that is quite often used, but yeah, there's a slight difference from my point of view. And yeah, if we look at the swarm, basically the definition of a swarm is that it's a large number of self-propelled entities, so in this case just robots, and they exhibit a collective behavior. So for example, like flying in the same direction towards a goal. Usually a swarm is defined by participants with rather basic skill levels. Then it's usually, or it's defined as a homogeneous group of agents, and a very important aspect, it's only a swarm if there's no central communication involved. We see on the other side the team. So a team is a rather small number of entities, and a very important aspect here is that a team tries to combine efforts to achieve a common goal. For this reason, it's also rather highly skilled agents. They can be heterogeneous, and here central coordination can be involved. So both are very interesting directions, but it might make a difference for the architecture what we go for. And if we think about the tasks that we were looking at, for example, search and rescue or industrial inspection, we would probably like not go for a huge swarm. And the idea is basically we want to combine efforts here. We would probably need highly skilled agents. So we are on the side of the teams, robotic teams for this talk, and we want to find now architectures for our robotic teams. And yeah, there's two main architectural paradigms that are used in the literature. So this is centralized systems and distributed approaches. And as you can see from the image here, or from the images, yeah, the defining characteristic of a centralized system is that we have this central instance. We call it the server or the ground station for this talk. And yeah, all the communication between the agents go through this central point. While in a distributed system, there's like pairwise communications between the agents without this central instance. And if we look a bit further on the details, so the centralized system has a nice advantage. We have this powerful server. We can outsource data and we can outsource computation to the central instance. The server adds some calculation power to our system in addition to the agents. And then, of course, like having all data stored at the central point simplifies data management for us. But of course, the clear downside is also that we need to pipe all information through the central point. So for like a lot of participants, a lot of data, this might become a bottleneck. Yeah, on the other side, we have distributed systems. They're spatially more flexible because they don't need to stay in like a communication distance to the server. Then, yeah, we don't have this bottleneck problem with the server, so it scales very well to a really large number of participants. The downside here is the global estimate is not present immediately, so we have to use some message passing between the agents to get a global estimate of our environment or of our formation. And of course, this distributed fashion of storing information makes it more difficult to keep consistency in the system. So yeah, if we think about our team of robots and the applications, especially like yeah, let's say industrial inspection, it's probably desirable to have a global estimate available directly, and also the idea to outsource computational load is very interesting to achieve a higher accuracy, for example, in the system. So yeah, for our architecture now, we will go for a centralized approach, or look a bit more into detail into centralized approaches. And yeah, of course, this is like not this is already present in literature. There are some approaches, and I want to quickly highlight some differences and see the pros and cons here. Yeah, one side that is used in some works in the literature is like I call it like we have a full SLAM system on the agent. So we see some building blocks of the SLAM system here. So the post tracking, creating a map of the environment, the map itself. So we keep a global map on board the agent, and also like a loop closure to see whether we revisit the location and the global optimization process, or global bundle adjustment in this case. All of this is run on board our agent. And then we have the server where we can fuse maps from different agents. We can store maps and maybe add another layer of optimization. And yeah, if we look at this, this clearly preserves the autonomy of the agent, because with the SLAM system, we have a full navigation stack already running on the agent. But on the other side, we keep also all the expensive algorithms there, like yeah, the global optimization. So this is not really like a efficient allocation of resources here, I would say. And then we see here the other extreme. So this is basically we perform only the post tracking on the agent, and all other parts of our system, including creating a map of the environment, we outsource to the server. This has the clear advantage that yeah, we can run with very limited computational resources on board the agent. We just have to perform yeah, localization against the known map that was shared from the server. Yeah, the downside is we cannot operate autonomously without the server. If the connection breaks, we don't get a map anymore. And also sending full maps all the time will cause a quite high network traffic in the end. So with these advantages and disadvantages in mind, I want to have a look at another architecture, and maybe we can keep the benefits and get rid of some of the disadvantages. And what we look at the beginning is the algorithms we run on board our robotic agent. And what we need here is a visual odometry. So what the visual odometry does, it estimates the ego motion of the robot, and yeah, the individual surroundings of the robot in terms of a local map. So we see here again our SLAM graph here with some keyframes and some 3D landmarks indicated. Yeah, and the first part here is the tracking. So the thing is, we have a local map, and then we have some incoming new camera frames. And of course, we need to estimate where they are in space so that we know how we have moved through the environment. This is what the tracking thread does. And then it decides whether we want to drop these frames or create a new keyframe from it and add it to our SLAM graph. The second part is mapping. So yeah, mapping, as the name says, it performs, it enters new landmarks in this local map using triangulation with our existing keyframes. And yeah, since it's a local map, so we keep only the immediate surroundings of our agent. This also performs trimming of the map, so we drop old experiences, old information that we don't need anymore on board the agent. And the final point is we want to also have a decent accuracy here so that we don't get totally off. So we need to employ an optimization scheme here. The optimization scheme here is called local bundle adjustment. I don't want to go too much into detail. Just the basic idea is we can project these landmarks into our image, in the images from the keyframes. And then we have this detection, this 2D feature locations, and the difference between the projection and these 2D key points. This we can call the reprojection error or reprojection residual ER. And what we do is basically we take this reprojection residual for all the keyframes and all the landmarks that we have in our local map. And then we try to minimize this error as an optimization problem. And with this, we can significantly increase the accuracy of our estimate. So this is the agent side of our system. We have a visual odometry, and now we look at the server. So basically the first point is we need to get this local map from the agent to the server somehow. So we need to add a communication module that bundles this in a message, sends it to the server, we retrieve it there, and then we put it in our map stack. So on the server we have this structure that we call the map stack, and it contains all the maps from all the agents, and they're not limited in size. It's all the information that was acquired during the SLAM session or the mission. And what we also need is a loop detection module. So this basically tells us if we come to a location where we have been before, and this way we can yeah, increase the accuracy of our estimate and reduce drift. So what we see here is basically a SLAM system that we have split between an agent side and a server side. And to make it a bit more clear what we're talking about, I want to show this video. So what we see here is like the agent map in green on a drone in this case, or a UAV, and the server map in white. And you see basically the map on the agent, it's only limited in size and drops all the experiences. And on the server side, we can keep all the information that we have acquired. And this is, yeah, basically what we have just seen, this part of the architecture in, yeah, deployed with like real world data. But of course, we want to have a collaborative system here. So we have to add another agent, right? So let's do that. We have a second agent. Of course, we get a second map in our map stack. So this is the idea of the map stack, having all the maps from all the agents. Yeah, but so far it's still not collaborative because, yeah, there's no connection between the maps, and we need to find this connection in terms of map matching and map fusion. What we do here is we use the visual information that we have extracted from the images. And yeah, this information we can basically use to calculate an alignment transformation between the maps, and then finally fuse them and make one map out of these two maps that we have before. So we can see here, this is like one map for both agents, and both of them contribute to it with their information now. And then the last point is what we need here is also some map management. So we have to refine the map, yeah, throw out some bad measurements, and of course we also need to employ an optimization scheme here. So this is the same thing that we did before. We minimize this reprojection error, reprojection residual, just that we do it now for all the keyframes and all the landmarks and all the agents, so all the data we have in the system. We solve this as a global optimization problem, and this is very beneficial for our accuracy. There's one point I quickly want to mention. So we can write this, this optimization problem in a bit another form. So we stack the variables that we have here, and then we can write this in this Gauss-Newton matrix form. We don't want to go too much into detail on it here, but we will need this formulation later. So I quickly want to mention it at this point. But yeah. Now we want to move on with our system. So there's one point that is missing. So we said before, we want the agent to be able to benefit actually from our shared data. And yeah, how can we do this? We have the last post of our agent here. And yeah, so we can take some information in the surroundings of this, this last post, which is probably the most valuable one for the agent. We send it back and augment the local map on the agent with this additional information. And yeah, right now we have this information in our map, and then if we want to estimate the position of data of new frames, we can do this using this augmented local map, and with this we can actually reuse the map information from the server on board our agent. And yeah, this is the architecture, and we can see here a proof of concept of a monocular collaborative SLAM system using this architecture. So we can see the maps on the server side, two maps for two agents at the beginning. And now we find overlap. We replace the maps with one shared map, and now both agents contribute to the same map with their experiences performing SLAM as a team. Another important thing is here we see some red landmarks. The interesting part about this is these are landmarks that are created by one agent, shared with the other agent, and reused there. So we can see that there is actually some collaboration and some data sharing taking place in this system. Yeah, so with this, I think we have a nice architecture which fits to our goals that we had before. The thing is, so far, this was only done like on one PC. It's run on data sets. And we want to see how we can move on to real world applicability here. So to show a bit the problem or the structure that we have. So far, this is what we have. We have like data from a robot or the algorithms that we want to run on board. And we have our server, and we simulate all these things with the data that we have pre-recorded on one PC, which is super nice. We have all communication going over the RAM of the PC. This is lossless and has almost unlimited bandwidth. So yeah, now we want to move on to a real world wireless setup. And here we get some other problems. So we have a message drop, we can have connection loss. Of course, these connections have latency, we have limited bandwidth. So we need to find ways to deal with this. And yeah, the first point is we need to find a way to reduce the data that we're sending. We call this an adaptive message passing scheme. So we see here again a local map, and if we look at one keyframe, we can basically figure out that like this contains a lot of data, which sums up altogether to around 60 kilobytes. And if we like constantly send like this whole local map with, let's say, 20 keyframes inside a few times per second, this will quickly exceed the bandwidth that we have here. But if we look a bit closer, we can figure out that actually most of the information is contained in these 2D key points and 2D feature descriptors. And actually those are measurements we take from the image. So they will not change anymore. So we don't need to resend them all the time. So what we do is we send this data only once, and from then on we send only information about changes. For example, if we change the pose of the keyframe, and with this we can significantly reduce the communication effort that we have in our system. Yeah, the second part is we need to find a way to get robustness to network effects. So network effects is the first one, is delay. So we can achieve here robustness through our architecture. So if we think of our architecture, there's no time dependency between agent and server. No one is waiting for information from the other in a specific time window. So this we have addressed. The other point is, yeah, we need to be robust to message loss, which can also happen. And yeah, we can achieve this through the communication protocol. There's two communication protocols. I don't want to explain them in depth. The point is there's basically this UDP protocol, which is very fast, but it doesn't guarantee that our data arrives. And we have this TCP protocol, which is a bit slower, but it takes care that all the data that we send arrives. So we have experimented with both, but in the end, we decided to go with the TCP protocol for our collaborative SLAM systems. It's slower than UDP, but still fast enough. We don't have issues here. And of course, since we are assuming that we send the measurements from the keyframes only once, we need to make sure that the data arrives at the other side. So this is the protocol of choice for us, and we have addressed message loss here. The last point is we have introduced the relative coordinate scheme so that we can ensure map consistency here. The problem is not visible from the beginning, but I will quickly explain it. So if we think about, we have our agent with our local map, and we have our server, and now we find a loop on the server side, and we want to actually optimize the map and improve it a bit so that we can get a better accuracy. But still, in the meantime, our agent is moving through the environment, creating new keyframes, sending them to the server. And yeah, we have them encoded in a world reference frame. And in the end, after the loop, after the optimization process is finished, parts of the map are shifted, but the data that has arrived during the optimization problem, these corrections do not arrive there since there's no connection to the existing map. So the map is inconsistent at the end, and this is not the thing that we want to have. So what can we do basically? What we do is, instead of encoding these keyframes in a world reference frame, we introduce a relative encoding. So we always encode their pose to a predecessor. So let's see what happens if the map gets shifted. The corrections are propagated to the new keyframes since they're connected by this relative pose, and we have a consistent map now, which is what we wanted. And yeah, let's see now how these communication strategies relate to real-world applications. So we see here the network traffic from a robotic agent to our server. And this is around 350 kilobytes per second, which is in an absolutely reasonable communication range, or in an absolutely reasonable range for what bandwidth wireless connections have. And an interesting aspect is, if we add more agents, the traffic is the same for each other agent. So adding agents to the system does not increase the communication effort for the individual agents. And this is a very important aspect for scalability. On the server side, we see something similar. The traffic is a bit higher, but also we have to say here, we can decide how much information we want to send back to the agent. So we can actually parameterize this if we have less network bandwidth available. What we see here that interestingly, the network traffic drops with more agents, what we might not have expected. The point here is we have more data, we have more agents. The optimization process takes longer, and during the optimization process, we cannot access the map, and therefore we have some time slots where we cannot send information to the agent. So actually the traffic drops a bit with multiple agents, but I want to emphasize there's no data getting lost here. And altogether, like all these communication strategies and this architecture that we have seen, we have implemented in a centralized collaborative monocular SLAM system that we call CCM SLAM. And yeah, now I want to show a video of CCM SLAM in a real world experiment, because this is actually what we wanted to prove here, that we can deploy collaborative SLAM in real world. So we have 3 drones with slightly different sensors, slightly different computation power. And yeah, we see here our setup. So we have the 3 drones, we have our server in the center, and what we see here is we see again the maps on the server side, so the server map of the first agent, and yeah, the second agent also, and then we can fuse the maps using the visual overlap. So we have now a shared map with both of these agents localized inside. And yeah, we wait for the third agent that is coming now. We do the same procedure, co-localization, and now we have a nice collaboratively shared map. So all agents contribute with their experiences to this map. Yeah, the agents are localized inside, so we are really performing collaborative SLAM. And the nice aspect is this is not done on data sets. This is really live in real time on board during the experiment. Yeah, this is what we wanted to show here. Actually, like for this CCM SLAM system, so if you're interested and you want to try it, you can try the code on GitHub. It's open source. And yeah, another video I want to show is we wanted to achieve platform independence. So we have also evaluated it with in a setup with a drone and a walking robot. So we see here again, these the robots perform their movements through the environment. They perform visual odometry, they share the information with the server. And yeah, at some point we can fuse the maps. We can create a collaborative map for this drone and the walking robot. So from then on, they are contributing again to the same map. So we have a collaborative SLAM estimate for a drone and a walking robot in a heterogeneous team. So let's look again at our goals that we wanted to achieve. So we have shown applicability in real world in heterogeneous teams, but yeah, there's some downsides. So we've seen a monocular system, so we don't have a metric scale estimate. The estimate is not aligned to gravity. So we can use it to estimate the motion, but actually we could not use this system to fly autonomously in the end. So we want to change that. And another important aspect is accuracy. So we want to also look at the accuracy now of the system. And yeah, to achieve good accuracy and our gravity alignment metric estimates, so far we had a camera-only system, and now we combine this, this architecture, this CCM SLAM system, with a visual-inertial sensor suite. So the idea is here, like the camera is an exteroceptive, outward-looking sensor. It has a low rate for a sensor from 20 to 30 hertz usually. And then we add the IMU, so the inertial measurement unit, which is a proprioceptive, inward-looking sensor that measures its own movement. It comes at a high rate from 100 to 200 hertz. And as we see at the bottom of the slide, this is actually like it adds information in between these camera frames, and the sensors have a nicely complementary nature. So yeah, this is a very good sensor setup to increase our accuracy. What we usually do is we take the IMU measurements between our frames and bundle them in such a in a packet for visualization. This is what we see here. And yeah, let's see how this affects our architecture. Of course, we have now as an input the IMU measurements also, which is a linear acceleration measurement and an angular velocity measurement. We augment our local map, of course, with these measurements that we're using. We extend the state, but we don't want to go into too much detail here. It's the only thing is we can now estimate also the velocity of our robot or of our keyframes, and there are some biases. You can imagine these as basically as an offset. This is not an additional information. We need this for accurately using our IMU information, and we have to estimate it. So we can use these IMU measurements, since we have information between the frames, to propagate the pose of the last frame or keyframe in the future, so that we have an initial estimate for the next frame that is incoming. And for the mapping, we can include these IMU constraints into our optimization. I think we don't want to go too much into theory here. The idea is just that we have, in addition to these reprojection residuals, we have now IMU residuals and also bias residuals to estimate the bias. And yeah, if we solve this problem, we can first get like the metric scale and the gravity direction, and we can achieve a higher accuracy this way. This is the underlying idea of including these IMU measurements. And then if we look at the whole system, of course, we have IMU measurements also in our server maps. And of course, we also include these IMU measurements and IMU residuals in our global optimization, which again improves significantly the accuracy of this estimation process or optimization process. So let's look at some actual numbers for the system. We call it a CVI SLAM, Collaborative Visual Inertial SLAM. We evaluated on the Europe dataset. This is a dataset that might not be familiar to everyone. So from this dataset, it's a flight of a small drone in an industrial environment, in an office environment. We use here the industrial environment. Yeah, the interesting part is we have a quite accurate ground truth here, so we can nicely evaluate the accuracy of our system. That's why we're using it. So the important, or the first aspect is like, if we look at the accuracy for single agent situations, so we can achieve comparable accuracy to other state-of-the-art methods, namely Visual-Inertial OBSLAM and WINS-MONO, what we have compared to. More interesting for us is, of course, the collaborative case. So what we look at is the error of the collaborative estimate at the end of the estimation process. So we have finished our mission, and we have a collaborative map, collaborative trajectory for multiple agents. So let's evaluate this. So we see here the result for two individual agents on two different sequences. So one has 8.5 centimeters of error, the other 6.3 centimeters of error. And if we perform collaborative SLAM using these two data sets, we can reduce this error to only 5 centimeters. So we can get a better accuracy for this estimate. Now, in a 4-agent scenario, things are not that clear from the beginning. For the single agent, we are between 0.06 and 0.08 meters of error, and it's 0.15 meters in the collaborative case. So we have to look a bit more into detail. If we look at the length of the trajectories, they are between like around 70 and 130 meters, while in the collaborative case, we're covering in total almost 400 meters of trajectory with our estimate. And if we now look at this in relation, so the relative error for our single agent cases is on average 0.08%, while in the collaborative case, this is half, 0.04%. So we can actually see here again the improvement of our estimate. So I think with these results, we can say collaborative SLAM improves the accuracy of our global estimate. Yeah, what we also wanted to evaluate is, can we actually see a benefit for the agent on board during the estimation process? So we evaluate the accuracy of the visual inertial odometry that we're using on board the agent. And what we see here, again, a single agent case. So we have 3 different combinations of 2 data set sequences. And the error for a single agent case, and in the multi-agent case, we can see through collaboration, through reusing data, we can in all 3 cases reduce this error. So we can say that collaboration in the end collaboration improves the accuracy not only after the estimation, but also online during our estimation process. So yeah, before we come to the last part of the talk, let me quickly summarize the key insights that we have seen about centralized collaborative SLAM. So I think we've talked a lot about the architecture, and the architecture is really important for an efficient and robust system. So yeah, it determines real-world applicability and platform independence. The architecture defines to which extent we can share, and to which extent we can reuse data, which is important for the collaborative aspect. And we have to choose the architecture in a wise way so that we can extend the framework easily. For example, in terms of the sensor setup, what we did, like extending it from a monocular to a visual-inertial setup. And then we have seen that collaboration and shared information can, of course, improve the accuracy of our global estimate, but also improve the accuracy of the local visual-inertial odometry estimates online during the mission. So with this, the last thing I want to talk about that we're missing is scalability. We've seen scalability in terms of network traffic. This works well, but there's the other side. This is the timings of the server, and especially our global optimization, which suffers a lot from the explosion of data. So I want to illustrate the problem a bit. We have this map, this nice map of the city of Zurich, and we want to get from the main station to the lake, which we have indicated here. This is around, I would say, like 1 kilometer, 1.5 kilometers. This is a thing a single agent SLAM system, I would say, could easily do these days. But yeah, let's imagine we want to cover like the whole city with our robot, and we're doing collaborative SLAM, right? So we want to do it with actually multiple agents. We've indicated 3 here. So this is now way too much data to handle it online in real time by a SLAM system. So what we need to find out is actually from all this data we have here, like if we take a piece of data like 1 keyframe here, like how much information does this keyframe actually add to our SLAM graph, to our SLAM estimate? Do we really need it, or can we actually get rid of this? Or in a bit more formal way, actually, we have here a SLAM graph and want to find a measure that quantifies how much information a piece of data adds to our estimate. And this is usually done using handcrafted heuristics, but we want to see how we can use notions from Shannon's information theory to get more accurate definitions for redundancy here. So we have to quickly look at our SLAM graph here. And the SLAM graph is, we see the landmarks and we see the keyframes. And what we can do here, we can introduce a notion of co-visibility, which means, if 2 keyframes are connected to the same landmark, we consider them as co-visible. And using this, we can actually define the co-visibility graph for keyframes that observe the same landmarks. And on this here, we define a Markov blanket. So this is basically all neighbors that are connected to a specific keyframe. And now we have to quickly come back to our formulation of bundle adjustment. We have this formula here that we don't need to go into detail again here. The point is we have here this Hessian matrix. And the interesting aspect is that the inverse of this Hessian matrix is the covariance of our system, the covariance of the individual keyframes. So we can have covariances for our individual keyframes. This is the important aspect we need to know. So using these 2 things, we can use a measure from information theory, which is called mutual information. The formula is basically there to just depict it depends on the covariances. So the idea of mutual information in simple words is basically if we have a high mutual information between, for example, 2 keyframes, this means if we know the pose of 1 keyframe, we more or less know also exactly the position, the pose of the other keyframe in simple words. While if this value is low, then basically 1 keyframe does not tell us much about the other one. And what we do here is basically for the neighbor of a keyframe, for all the neighbors, we calculate this value, we sum it up and average it, and this gives us a measure for information, like how much information this specific keyframe adds to its neighbors in the graph. So there's a problem with this measure. So it's a measure between 2 neighbors. So the information can be also incorporated in other neighbors here. And this might be a problem for our measure. we can do something about this. So we see here again our co-visibility graph. I want just to briefly give the idea. So we can stitch a covariance matrix for this piece of the graph, and then we can calculate the conditional covariances for these keyframes I and j that we're looking at now. So basically what we do here, we can isolate the information that is shared between these keyframes I and j, assuming that we know the information that is encoded in the other keyframes. This is the basic idea. So yeah, the idea is now we use this conditional covariance matrices to calculate the conditional mutual information measure. So again, in a bit simpler words, the idea is here, we extract the information that is only shared between these keyframes I and j, and is not contained in any other neighbor. This is why we're using the conditional covariances. And then again, we sum this up, we average it, and this gives us our information value. So yeah, this is the basic idea. And yeah, I want to show an evaluation now, what the effect of this is. So this is actually like, again, our Europe data set. This is 2 sequences. They're called MH1 and 2 for machine hall. It's the industrial environment. The interesting aspect here is we have 585 keyframes in our system, and we want to compress this graph with 585 keyframes to a graph with 300 keyframes and a graph with 200 keyframes in 2 experiments. And the green bar here actually indicates our baseline. So 585 keyframes have 2.5 centimeters of error on the trajectory. The first thing we do is actually we just randomly remove some keyframes, which ends up in an increase in the error. And of course, yeah, we should perform better than random with our strategies. Otherwise, we're most likely doing something wrong. So first, we want to evaluate some heuristics. The first one is a heuristic from OpSLAM, which is yeah, one of the state-of-the-art SLAM systems out there. We see for 300 keyframes, there's not much change. For 200 keyframes, we have a significant increase. We have another heuristic for that we have proposed together with these mutual information-based measures we're actually looking at. Yeah, we see also here it performs a bit better than the other heuristic, but there's still a significant increase in the accuracy. So let's look at the mutual information measures. So the first one is the like a classic mutual information. Yeah, what do we see here? Actually, in the 200 keyframes case, we don't get much from it compared to the other heuristic. In the 300 keyframes case, it actually, the error increases. Yeah, but we have identified that there might be the problem of that the information might actually be encoded in the neighborhood. So let's look at our conditional mutual information measure. And actually here we see that in both cases it performs best. It's better than the original mutual information, which indicates that yeah, that there is information in the neighbors that we need to consider. It performs also better than the heuristics. And also the increase in error is not that much. So we can actually, we have in the right case, we have almost only 1/3 of keyframes, but yeah, not that much increase in the error, which is a very nice aspect. So yeah, the key insights here is we can use information theoretic approach for redundancy detection to quantify the information that is contributed from keyframes in our graph. We can outperform handcrafted heuristics using information theory, and we can enable large graph compressions with only minimal loss in accuracy using these type of measures. And yeah, with this, we're coming to the end of the talk. So let me quickly wrap up what we have seen. So the first point is the underlying architecture is the cornerstone for practical and efficient multi-agent system. So yeah, the architecture determines scalability of the system and the depth of the collaboration, and it's key for real-world applicability. We have seen how centralized collaborative SLAM leverages the full potential of robotic teams. It enables the full spectrum of possibilities in a multi-robot system and allows to make the most of the agent's individual experiences. And yeah, we have seen that efficient data handling and removal of redundant data is crucial to handle the huge amount of information that we have in multi-agent systems. So of course, the problem of collaborative SLAM or collaborative perception is not solved here. There's a lot of things that we still have to do. So the first thing is here we have seen all the experiments with high quality sensors, global shutter cameras, IMUs with quite low noise level, but it would be nice to actually move to, for example, consumer level hardware like smartphones, a very interesting direction. It opens up many possibilities for our system. On the other side, it's quite challenging since, yeah, this is sensor data of much lower quality, for example, higher sensor noise, higher noise on the IMU, more motion blur on the camera. So we have to deal with this somehow. And also interesting direction would be to investigate cloud computing, since we can have much more calculation power here than we could have on a single computer that we use as a server. The second part is data management. So we have seen how data management and redundancy detection and removal increases the scalability of our system. And of course, if we could improve the detection of redundant data and remove more data, this would boost even further our scalability. We have seen how we can use information theoretic approaches for this. The downside of the information theoretic approaches right now is they're quite computationally heavy, so we cannot run them in real time. And of course, this would also be an interesting direction to pursue. If we can get more efficient here, we might be able to actually perform this also in real time online at some point. And the last aspect I want to highlight is viewpoint tolerance. So we have seen collaborative SLAM with the drone and the walking robot, but let's add another robot here, which is this Croc 2 salamander-like robot on the ground. We can see here the viewpoint is extremely different between the three robots, and this is actually beyond the level of viewpoint tolerance that state-of-the-art vision algorithms can handle to localize, co-localize these robots. So if we want to leverage heterogeneous robotic teams, we have to tackle this problem of viewpoint tolerance. And then in the long term, of course, if we have collaborative SLAM, this provides our robots with the position of its peers and a shared map. This opens up many directions for our robotic team. The first one is, for example, fleet coordination. So we might want to plan paths for all the robots in the team, for example, to maximize coverage and efficiency when we are reconstructing a structure of interest. Or we can even go one step further to multi-agent interaction. So imagine we have a search and rescue scenario. We have our agile airborne robots that can quickly explore the environment and then share this map that they've built with ground robots which have lower mobility but much higher payload. They don't have to do exploration anymore. They get information about the victims and, for example, structures that are in danger to collapse. So they can directly provide first aid there and stabilize structures. And also a very interesting direction that I see here is the recent developments in AR or VR technology. So if we think these devices are also usually equipped with cameras and calculation power, communication devices. So we can actually use this to create collaborative SLAM with these devices to create a shared augmented or virtual reality experience for multiple users, like it's depicted here in this example with like a house model that these two users are looking at and share in their view. So with this we have seen both theoretical and practical aspects of multi-agent SLAM and how we can drive the systems to further maturity and to further robustness and allow robots to perceive their environment as a team. And with this I'm done with the talk. Thanks a lot for your attention, and I'm happy to answer some questions if there are some.
Thank you very much for the really interesting talk. Are there questions for the audience? No questions? Right, I have two. I mean, I'm not an expert of the field, but I have two questions. Sure. So I have a background in, okay, let's start with this first one. So some while ago I worked, for example, on autonomous calibration of sensors. And do you think that there is I see a potential application also there, right? If you're able to share knowledge about the environment by knowing the position of the other robots, you can exploit this to do online calibration for various type of sensors. Or what do you think about that?
Yeah, I think, of course, for the co-localization, it's always beneficial to have very well calibrated sensors. But yeah, I think if you compare it, like if you have only one robot or if you have two robots looking at the same thing and you could share information, I think you could probably also include that in the online calibration process. Yes, I would imagine that. I think probably like the calibration you would have to do, like, let's say in the background. So I would imagine this is a more like a computationally expensive process. So maybe it's not so actually we're not doing like online calibration right now with the system. So I have to also, I'm not an expert on it, but I would say probably you could use the information, especially if you know that you're, like, for example, if you're looking at a structure that you already know, I think then it would be quite helpful.
Yeah, very interesting. And yeah, the second, it's more a thought than a question. It's very interesting because now when you think about, for example, autonomous vehicles, which is the field where I'm working in, you have to choose the size of the fleets, for example, or you have to choose where to send the different robots. And now there is another factor, which is how to diversify the fleets. Maybe there are some autonomous vehicles that are just meant to help the other vehicles doing SLAM and not bring any customers, for example. And I think it's really interesting because also it opens up problems of fleet sizing of robots which are doing collaborative SLAM, for example. So,
okay, so you mean basically, for example, like some cars that are just, let's say, there to explore some areas and refine a map, but not for customers.
Yeah, for example.
Okay, yeah.
That could be also interesting. Or
I think basically yeah, I've tried to quickly touch on that in the end. So I would say like my work is really more on the side of yeah, I tend to say it's like a passive system. So we only do like estimation here. We don't actively steer the robots. And I think now we came to a state that we're trying to actually build also planning algorithms on top of it. And I think there's really a lot to get if you can then use the estimates to actively steer the robot somewhere. I think this is a super interesting direction. I'm really curious, like what we will see like coming on top of this, like how we can actively use this yeah, fleets of robots. I would totally agree.
That's very, very interesting. Imagine autonomous cars with drones on top of the car and releasing the drones before exploring unknown environments.
Yeah, that would be really cool. Yeah.
Very, very interesting. Very interesting. Are there other questions from the audience? From the reduced audience today? No, I don't think so.
Yeah,
so
I think Patrik, otherwise, I think if you put the talk online, I mean, the mail address is easy to find, so people are welcome to ask questions also on other channels.
Exactly.
Cool.
Thank you very much then for giving the talk. I will send you the video once it's edited. And
cool. Okay.
Good luck for the future of the research. Very, very interesting.
Yeah, thanks a lot. Thanks for the possibility to give the talk in the format.
Thank you.
Good. So thanks a lot.
Have a good night. Bye-bye. Thank you.
Bye-bye.